systems analysis and design by the Routh Locus method. Hello everyone, my name is Rafael. I am an electrical engineer, and in this video we are going to speak about the Routh Locus method. Let's see the technique. First of all, we are going to see an introduction that's going to help us understand the purpose of using this technique. The basic characteristic of the transient response of a closed-loop system is closely related to the location of the closed-loop poles. If the system has a variable loop gain, then the location of the closed-loop poles depends on the value of the loop gain chosen. It is important, therefore, that the designer know how the closed-loop poles move in the S-plane as the loop gain is varied. From the design viewpoint, in some systems, simple gain adjustment may move the closed-loop poles to desired locations. Then the design problem may become the selection of an appropriate gain value. If the gain adjustment alone does not yield a desired result, addition of a compensator to the system will be necessary. The closed-loop poles are the roots of the characteristic equation. Find the roots of the characteristic equation of degree higher than 3 is laborious and will need computer solution. However, just to find the roots of the characteristic equation may be of limited value because as the gain of the open loop transfer function varies, the characteristic equation changes and the computations must be repeated. A simple method for finding the roots of the characteristic equation has been developed by W.E. Evans and used extensively in control engineering. This method, called the Routh Locus method, is one in which the roots of the characteristic equation are plotted for all values of a system parameter. The roots corresponding to a particular value of this parameter can be then located on the resulting graph. Note that the parameter is usually the gain, but any other variable of the open loop transfer function may be used. Unless otherwise stated, we shall assume that the gain of the open loop transfer function is the parameter to be varied through all values from 0 to infinity. Okay, my friends, this is the introduction, the motivation behind the Routh Locus method, and we are going to see some other parameters and concepts before seeing an example. Routh Locus plots angle and magnitude conditions. Consider the negative feedback system shown in figure 6-1. The closed loop transfer function is C of S divided by R of S equal to G of S divided by 1 plus G of S times H of S. And this figure here shows the block diagram for the closed loop transfer function. The characteristic equation for this closed loop system is obtained by setting the denominator of the right-hand side of equation 6-1 equal to 0. Then, here we have the characteristic equation, and what we are going to do is to set it, the denominator only, we are going to set it to 0. That is 1 plus G of S times H of S is equal to 0. Or in a different format, g of s times h of s is equal to -1. Here we assume that the g of s times h of s is a ratio of polynomials in S. Since g of s times h of s is a complex quantity, equation 6-1 can be split into two equations by equating the angles and the magnitudes of both sides, respectively, to obtain the following. Then, the angle condition, let's take a look at the angle condition. The angle of g of s times h of s has to be equal to plus minus 180 degrees times 2k plus 1, where k is a natural number, positive natural number, 0, 1, 2, 3, etc. And the magnitude condition is the absolute value of g of s times h of s has to be equal to 1. So these are the conditions, the angle condition and the magnitude condition. Now let's see how we can use this. There is an additional information about this. Let's see what the book speaks about. The values of S that fulfill both the angle and magnitude condition are the roots of the characteristic equation or the closed loop poles. A locus of the points in the complex plane satisfying the angle condition alone is the root locus. The roots of the characteristic equation, the closed loop poles corresponding to a given value of the gain, can be determined from the magnitude condition. The details of applying the angle and magnitude conditions to obtain the closed loop poles are presented later in this section. Okay, we are going to jump here because knowing this is not necessary. We are going to go straight to the example. Okay, there is going to be an example here that will tell us more about this technique. Now let's see the example. Consider the negative feedback system shown in figure 6-3. Let's see the figure. Okay, this is figure 6-3. So this is what we are going to work with, this block diagram here. Can you guys see it? It's this block diagram here. Let's see what the problem speaks about. Consider the negative feedback system shown in the figure. We assume that the value of gain k is non-negative. For the system, g of s is equal to k divided by s times s plus 1 times s plus 2, and h of s is equal to 1. Let's see if it is true. Let's return to the image. Yes, in reality, as you can see, k here divided by s times s plus 1 times s plus 2 is g of s. And as you can see that the output c of s is being directly fed into the adder, then h of s is equal to 1. Okay, that's true. The book is telling the truth. Okay, now let's sketch the root locus plot and then determine the value of k such that the damping ratio xi, do you guys know this letter, this Greek letter xi? It is the damping ratio, and such that the damping ratio of a pair of dominant complex conjugate closed loop poles is 0.5. So for us, xi is 0.5, the damping ratio. Now let's analyze the conditions, the angle condition and the magnitude condition. For the given system, the angle condition becomes the angle of g of s times h of s is simply the angle of g of s, because h of s, as we saw, is equal to 1. The angle of g of s is equal to the angle of k divided by s times s plus 1 times s plus 2. And this is going to be equal to the negative of the angle of s minus the angle of s plus 1 minus the angle of s plus 2. And why the negative sign, you ask me? The negative sign is because they are in the denominator. If they were in the numerator, then the sign would be positive. As they are in the denominator, then the sign is negative for angles only, not for magnitude, only for angles. And then their angle together shall be equal to positive negative 180 degrees multiplying 2k plus 1, where k is equal to 0, 1, 2, 3, etc. The magnitude condition is the magnitude of g of s is the magnitude of k divided by s times s plus 1 times s plus 2 equal to 1. Okay, now that we know the magnitude condition and the angle condition, let's start. A typical procedure for sketching the Routh locus plot is as follows. First step, determine the Routh loci on the real axis. The first step in constructing a Routh locus plot is to locate the open loop poles s equal to 0, s equal to negative 1, and s equal to negative 2 in the complex plane. Okay, how do we know that? How do we know that the poles are s equal to 0, s equal to negative 1, s equal to negative 2? We see here in the denominator that we have s multiplying s plus 1, and s plus 2. The root of this characteristic equation will be when the denominator is 0. To make the denominator 0, we can simply put 0 here for this s. When this s is equal to 0, then we have a 0 in the denominator, which is actually the pole of the closed loop transfer function. And for this part here, s plus 1, a 0 would be negative 1, because negative 1 plus positive 1 is 0, and then we have another pole. And for this part here, s plus 2, to have a 0 there, we need to have a negative 2, because negative 2 plus 2 is equal to 0. Then we have justified the reason the book said that the poles are s equal to 0, s equal to negative 1, and s equal to negative 2. Okay, let's continue. There are no open loop zeros in this system. Why there are no open loop zeros in this system? Because k is a number. K is not a function of s. If k were multiplying a function of s in the numerator, then we'd have a open loop 0. But as k does not multiply anything as a function of s in the numerator, then we don't have an open loop 0. Okay, that's the justification. The locations of the open loop zeros in this book will be indicated by small circles. So, in the plot, zeros are small circles. Note that the starting points of the Routh loci, the points corresponding to k equal to 0, are open loop poles. The number of individual root loci for this system is 3, which is the same as the number of open loop poles. Okay, let's see the loci of the root here. To determine the root loci on the real axis, we select a test point. It is important that you understand this step. We need to select a test point. If the test point is on the positive real axis, then the angle of S is going to be equal to the angle of S plus 1, and they are going to be equal to the angle of S plus 2, which is 0. Okay, because they are at the positive real axis. This shows that the angle condition cannot be satisfied. Why not? Tell me, why not? Why isn't the angle condition satisfied? Because we saw here that for the angle condition to be satisfied, uh, the angle has to be a multiple of 180 degrees, multiplying 2k plus 1. And that condition is not satisfied here. Okay? 0 is not a multiple of 180 degrees times 2k plus 1. All right. Hence, there is no root locus on the positive real axis. Next, select a test point on the negative real axis between 0 and negative 1. Then, the angle of S is 180 degrees. The angle of S plus 1 is equal to the angle of S plus 2, which is 0 degrees. And if we sum the angles, the angle of negative the angle of S minus the angle of S plus 1 minus the angle of S plus 2 is equal to negative 100 degrees. And the angle condition is then satisfied. Okay? Very good, very good. We found a place where the angle condition is satisfied. Let's continue. There are more places, portions of the real axis where the angle condition is satisfied. Therefore, the portion of the negative real axis between 0 and negative 1 forms a portion of the root locus. If a test point is selected between negative 1 and negative 2, then the angle of S is equal to the angle of S plus 1, which is 180 degrees. And the angle of S plus 2 is equal to 0. If we sum the angles, minus the angle of S minus the angle of S plus 1 minus the angle of S plus 2 is equal to negative 360 degrees. And the angle condition, one more time, is not satisfied. And it can be seen that the angle condition is not satisfied here. Therefore, the negative real axis from negative 1 to negative 2 is not a part of the root locus. Similarly, if a test point is located on the negative real axis from negative 2 to negative infinity, the angle condition is satisfied because, again, the angle is going to be a multiple of 180 degrees times 2k plus 1. Okay. Does root loci exist on the negative real axis between 0 and negative 1 and between negative 2 and negative infinity? Okay, now that we know this, we can move ahead and we can try to know more about how to plot the root locus for this example. The asymptotes of the root loci as S approaches infinity can be determined as follows. If a test point S is selected very far from the origin, then The limit of g of s when s approaches infinity is equal to the limit when s approaches infinity of k divided by s times s plus 1 times s plus 2, which is the limit of k divided by s cubed when s approaches infinity. And the angle condition becomes, okay, as we are using a very big number for s, let's understand this expression here before moving on. As we are using a very big number for s as s approaches infinity, then you can neglect this one here and you can neglect this two here. And then the expression is going to be reduced by this. Okay? Because s plus 1, for example, let's use a big number, 1 billion. 1 billion plus 1 in our purposes here is equal to 1 billion. If you add 1, you are not going to alter much the characteristic of the number. That's why the book says it's better we use this expression here, k divided by s cubed. And the angle condition becomes uh, negative 3 times the angle of s, which is equal to a positive and negative 180 degrees, times 2k plus 1, and k equal to 0, 1, and 2. This is, one more time, the angle condition that needs to be satisfied. Angle of asymptotes, positive, negative 180 degrees, 2k plus 1 divided by 3 because of this 3 here, and this 3 here is linked to this 3 here of the expression k divided by s cubed. And since the angles repeat itself as k is varied, the distinct angles for the asymptotes are determined as 60 degrees, negative 60 degrees, and 180 degrees. Thus, there are three asymptotes. The one having the angle of 180 degrees is the negative real axis. Okay, and before we draw these asymptotes in the complex plane, we must find the point where they intersect the real axis. To do so, we are going to use this technique here. One more time. G of s, which is the characteristic equation, k divided by s times s plus 1 times s plus 2. If a test point is located very far from the origin, then g of f may be written as g of s is equal to k divided by s cubed plus 3 times s squared plus. We're going to develop this denominator here. Okay, only the denominator. We're going to develop this denominator here, and then we're going to find an expression here in the denominator. The book says that it is better we approximate this by this. Okay, this new expression here. The book saying that for very large values of s, okay, when s approaches infinity, it is the same as s plus 1 cubed. Okay, k divided by s plus 1 cubed. This is what the book is advising us to do. A Routh locus diagram of g of s given by equation 6-5. This equation highlighted here consists of three straight lines. This can be seen as follows. The equation of the Routh locus is k divided by s plus 1 cubed is equal to plus minus 180 degrees to k plus 1, or negative 3 times the angle of s plus 1 has to be equal to, this is the angle condition, positive negative 180 degrees, 2 times k plus 1, which can be rewritten as s plus 1 equal to plus minus 60 degrees to k plus 1. We took this negative 3 here, and then we divided the number 180 degrees by negative 3. Okay? And we are going to substitute s by sigma plus jw into this last equation. We obtain that the angle of sigma plus jw plus 1 is equal to positive negative 60 degrees to k plus 1. And then the inverse tangent of sigma, the inverse tangent of w divided by sigma plus 1 is equal to three angles here, 60 degrees, negative 60 degrees, and 0 degrees. Taking the tangent of both sides of this last equation, we find w divided by sigma plus 1 is equal to the square root of 3. W divided by sigma plus 1 is equal to negative the square root of 3. And w divided by sigma plus 1 is equal to 0, which can be written as, so these are the lines. These are the lines. This, and this. These are the lines, okay? The asymptotes that we are looking for. Sigma plus 1 minus w divided by the square root of 3 equal to 0. Sigma plus 1 plus w divided by the square root of 3 is equal to 0. And w equal to 0. These three equations represent three straight lines. Okay? Three straight lines. And the figure 6-4 shows it. Okay? Let's take a look at the figure 6-4. We have here three lines. W equal to 0 is this line here from negative 1 to negative infinity. Sigma plus 1 minus w divided by 3 equal to 0 is this line here, which begins at the negative 1 in the real axis and crosses the imaginary axis at j times the square root of 3. And the other line, sigma plus 1 plus w divided by the square root of 3 equal to 0, begins at negative 1 in the real axis and crosses the imaginary axis at negative j times the square root of 3. And the three straight lines shown are the asymptotes. They meet at point s equal to negative 1. Thus, the abscissa of the intersection of the asymptotes and the real axis is obtained by setting the denominator of the right-hand side of equation 6-5 equal to 0 and solving for s. The asymptotes are almost parts of the root loci in regions very far from the origin. Okay, let's continue. Let's talk about the breakaway point. Step number 3, the breakaway point. Okay, this is a very interesting part of this because the breakaway point is the point of largest gain, okay, of largest gain in the real axis. Okay, when we have the largest gain, when the derivative of the gain with respect to s is equal to 0, a point of maximum, then we have a breakaway point. Let's see what the book says. To plot root loci accurately, we must find the breakaway point where the root locus branches originating from the poles at 0 and negative 1 breakaway, as k is increased from the real axis and move into the complex plane. The breakaway point corresponds to a point in the S-plane where multiple roots of the characteristic equation occur. A simple method for finding the breakaway point is available. We shall present this method in the following. Let us write the characteristic equation as, okay, the characteristic equation is going to be f of s equal to b of s plus k times a of s equal to 0, where a of s and b of s do not contain k. Note that f of s has multiple roots at points where the derivative of s with respect to s is equal to 0. And this can mean as follows. Suppose that f of s has multiple roots of order r, where r is greater or equal to 2. Then f of s may be written as, all right, my friends, this is the technique that the book is presenting. I don't think it is straightforward. I have consulted other materials by MIT, which is considered the best school of engineering in the world, and they have demonstrated to me that the best technique to find the breakaway points is to assume that the angle, the gain has a maximum at the breakaway point. And this book here is going to gravitate around this technique as well, but this book follows other procedures. And then the book says that now it differentiated this equation with respect to s and evaluate the derivative of f of s with respect to s at s equal to s1. Then we get this, and we set it to 0. This means that multiple roots of f of s will satisfy equation 6-7. From equation 6-6, we obtain that the derivative of the function with respect to s is the derivative of b of s, which is b prime of s, plus k times a prime of s equal to 0, and then we find these expressions for a prime of s and these expressions for b prime of s. And here, I'm going to jump these procedures here, and then I'm going to highlight the main result. The main result is this, okay? I'm going to return this. The main result is this here. The derivative of the gain with respect to s has to be equal to 0. And the book says that if the derivative of k, the gain, with respect to s is set equal to 0, we get the same equation. Therefore, the breakaway point can be simply determined from the roots of it. And then we get at what MIT, the best school of engineering in the world, says that whenever we have a maxima of gain, we have the breakaway point. And we are going to use this technique to find the breakaway point now using this example. For the present example, the characteristic equation g of s plus 1 is equal to 0 is given by k divided by s times s plus 1 times s plus 2 plus 1 equal to 0, or k equal to negative times minus s cubed plus 3 times s squared plus 2 times s. By setting the derivative with respect to s equal to 0, we obtain that s is equal to negative 0.4226 and s equal to negative 1.5774. So these are the points that we discovered by using this technique, but not every one of these points will be the breakaway point, and we shall see why. Since the breakaway point must lie on a root locus between 0 and negative 1, it is clear that s equal to minus 0.4226 corresponds to the actual breakaway point. s equal to negative 1.5774 is not on the root locus. Okay? Could you understand the condition? The breakaway point must lie on a root locus between 0 and negative 1. That's why s equal to minus 1.5774 does not pertain to the root locus, and it is not the breakaway point. Hence, this point is not an actual breakaway point or breaking point. In fact, evaluation of the values of k corresponding to s equal to minus 0.4226 and s equal to minus 1.5774 yields k equal to 0.3849 for s equal to negative 0.4226 and k equal to negative 0.3849 for s equal to negative 1.5774. Okay, then we know now that this is the breakaway point. The other is not. Only this one here is going to be the breakaway point. And number 4, to determine the points where the root loci cross the imaginary axis. We are going to find the points where the root loci cross the imaginary axis. And to do so, we are going to use Routh stability criterion. These points can be found by use of Routh stability criterion as follows. Since the characteristic equation for the present system is s cubed plus 3 times s squared plus 2 times s plus k equal to 0. And what is the objective of using Routh's stability criterion? If all values are positive, then we need uh, solutions to have imaginary numbers. And we know that imaginary numbers produce stabilities, and they need to be on the left-hand side of the complex plane. Okay? And exactly at the imaginary number, we are going to have uh, points where the roots are zero. The roots are zero. Okay, they are going to cross the imaginary axis at points where the real axis is zero. The value in the real axis is zero. Then we're going to use this technique here. For s cubed, we put 1 and 2. For s squared, we put 3 and k. For s1, 6 minus k divided by 3. And for s0, k. And then we are going to use that this expression here, 6 minus k divided by 3, has to be equal to 0. We are going to set it to be equal to 0 to find the point exactly where the root loci were across the imaginary axis. The value of k that makes the S1 term in the first column equal to 0 is k equal to 6, okay? The crossing points on the imaginary axis can then be found by solving the auxiliary equation obtained from the S squared raw, that is 3s squared plus k, which is 3s squared plus 6 equal to 0. And then we find solutions for this equation as s equal to plus minus j times the square root of 2. The frequencies at the corresponding points on the imaginary axis are thus w equal to plus minus the square root of 2. The gain value corresponding to the crossing points is k equal to 0. So, at the crossing points on the imaginary axis, the gain is equal to 6. Okay, the book is going to talk about an alternative approach here. I don't think it is necessary. Let's move on. Let's move on to the other step towards sketching the root locus plot. Okay, choose a test point in the broad neighborhood of the JW axis and the origin, as shown in figure 6-5. 6-5 is this image here. We are going to select test points. This is here, this guy here, this guy is the test point, okay? And we are going to use test points here to check if the condition satisfies. Choose a test point in the broad neighborhood of the JW axis and the origin, as shown in the figure, and apply the angle condition. So we need to use the angle condition to see if it is satisfied. If it is not, we are going to discard this portion of the complex plane. If a test point is on the root loci, then the sum of the angles theta 1, theta 2, and theta 3 must be equal to 180 degrees. If the test point does not satisfy the angle condition, select another test point until it satisfies the condition. The sum of the angles at the test point will indicate the direction in which the test point should be moved. Continue this procedure and locate a sufficient number of points satisfying the angle condition. Okay, and now we are going to draw the root loci based on the information obtained in the foregoing steps as shown in figure 6-6. Okay, there are many things here that we can see. First of all, see that as we calculated the root loci along the real axis will be from 0 to -1 and from -2 to -infinity. However, the root locus uh, crosses, goes beyond the real axis and goes into the complex plane, having imaginary components. And here, the breakaway point is exactly here. Okay, exactly this point here, the breakaway point, okay, where the angle along the real axis has a maximum. And we also calculated the asymptotes. The asymptotes are these lines here, -1, beginning in -1 and crossing the imaginary axis at -j. Let me remember, it was -j square root of 3, okay? And the other one will cross the imaginary axis at -j times the square root of 3. And then we have the point where the root locus crosses the imaginary axis, and it is going to be the points. Let's remember the points where it crosses the imaginary axis. Okay, choose a test point, draw the root loci, cross the imaginary axis. We found it here. Okay, step number 4 is the step for calculating this, and we discovered that they cross at positive and negative square root of 2. Okay, so going back to the point, this is going to be the points where for for the gain equal to 6, where they will cross the imaginary axis. And so this is the root locus for this exercise, okay? And there is going to be another step that will cover the condition, the initial condition of the problem, which says that C, the damping ratio, has to be equal to 0.5. And then the last step, step number 7, determine a pair of dominant complex conjugate closed loop poles such that the damping ratio C is equal to 0.5. Closed loop poles with C equal to 0.5 lie on lines passing through the origin and making the angles plus minus the inverse cosine of C equal to plus minus the inverse cosine of 0.5, which is equal to plus minus 60 degrees with the negative real axis. From the figure 6.6, such closed loop poles having C equal to 0.5 are obtained as follows. Okay, we are going to see where in the graph we have these angles positive and negative 60 degrees. Oh, they are here. Okay, this line is here, and this line here and here, and they are going to cross the root locus at the gain k equal to 1.0383. And let's see the purpose of finding this gain. Okay, we want a damping ratio to be equal to 0.5. And from the figure, close to equal to 5 obtained as follows. S equal to negative 0.3337 plus J 0.5780, and S2 equal to negative 0.3337 minus J equal to 0.5780. You can see they are complex conjugate, because the only difference is here in the imaginary part. One is positive and the other is negative. The value of k that yields such poles is found from the magnitude condition as follows. Okay, the gain is going to be equal to the magnitude of s times s plus 1 times s plus 2, for s being equal to one of the poles. And if you substitute s by one of these complex conjugate poles, we find a gain of 1.0383. Using this value of k, the third pole is found at s equal to minus 2.3326. Let's see if we find this. Okay, one pole is going to be for the gain here. So we have one pole here, we have one pole here, we have one pole here, and we have another pole here for this gain 1.0383, and this gain was found for the condition of C being equal to 0.5. Note that from step 4, it can be seen that for gain k equal to 6, the dominant closed loop poles lie on the imaginary axis at s equal to plus minus j times the square root of 2. With this value of k, the system will exhibit sustained oscillations. For k greater than 6, the dominant closed loop poles lie in the right half as plane, resulting in an unstable system. Finally, note that if necessary, the root loci can be easily graduated in terms of k by use of the magnitude condition. We simply pick out a point on a root locus, measure the magnitudes of the three complex quantities s plus 1, and s plus 2, and multiply these magnitudes, the product is equal to the value to the gain value k at point, or the magnitude of s times the magnitude of s plus 1 times the magnitude of s plus 2 equal to k. All right, my friends, this was the video about the root locus technique for system stability. Okay, my friends, I am a teacher and consultant. If you guys want to book a lesson with me, do any kind of service, request any kind of service related to engineering and energy markets and industrial automation, you can contact me using my WhatsApp number, guys. Goodbye.